everyone for coming. Really happy to introduce Roman Fedorov, who's visiting from from some department in the Politecnico di Milano. Okay, I was told I can't translate it. I was going to translate it, but that's
so it's Politecnico, Politecnico University.
This is great. And so he's a PhD student there, and he's working on some really interesting work that combines together environmental sensing and computer vision and lots of things together. It's kind of exciting as a computer vision person. I don't know how you feel, Michael, but it's exciting that suddenly vision works well enough to actually be useful in applications like this. Kind of says something for how much progress we've made. So thanks so much for coming, and really looking forward to your talk.
Okay, so hi to everybody. Yeah, as Professor Crandall just introduced, I'm from Politecnico University of Milan. I work in the research group of Data, Web and Society with Professor Fraternali, which basically is focused on all the aspects of web data analysis and crowdsourcing. So both passive crowdsourcing, so analyzing user-generated content, like I do, and I have colleagues also that focus on active or traditional crowdsourcing, both in the most traditional way, such as pay people and study all the aspects of how to pay, who to pay, whatever, and also how to engage in alternative ways, so gamification and all the aspects. So I'll try to cover a bit. And today, I'm going to speak about how to apply computer vision techniques to the data mining of publicly available images to improve the environmental monitoring. And we work on this aspect in several fields, like snow, water, and vegetation, but snow in particularly is the most mature project, so I'm going to speak mostly about it and then briefly illustrate all the other fields. Okay? So the first is to introduce the user-generated content. I think that I always present this slide, but I think that it's almost useless in this room because it's basically the job of everybody here, right? But still, we analyze the media, user-generated content available publicly on the web, which is reaching incredibly mass, like 350 billion of daily photo uploads on Facebook, 8,000 uploads total, 8,000 million on Flickr with 3 million daily uploads, and Panorama, for example, which is a bit smaller photo sharing website, but still concentrated on all the outdoor things, so very useful for environmental and ecological monitoring, has more than 75 millions of geotagged photographs. Okay, so all this media content contains some kind of knowledge also about the environmental, the ecological world, and we would like to extract it. Yeah, so the challenge in particular is to extract these environmental related data from timestamp and geolocated images that are publicly available, that were generated by people or by sensors, and to use this data to complement existing measurements of environmental monitoring. Okay, so clearly we do not want to substitute our measurements to the traditional ones, but still we state that there is a lot of room for improvement to complement different sources of environmental data. And as I said, in particular, the main project is called SnowWatch, and it aims at improving snow analysis, and with snow analysis also the management of the water available from it, from the publicly available images of alpine mountains, such as both photographs uploaded on photo sharing platforms and publicly available webcams, such as touristic or ski resort webcams, and create a huge data set of these images with all the related metadata and annotations, okay, that could be useful both to environmental engineers and also to IT engineers, like those in this room, to study further improvements. So, taking a big picture of it, what SnowWatch is some kind of layer that do acquire media content from what we call content providers, analyze it somehow, store it with enriched data, and then provide it to content consumers. Okay? In particular, the system is extremely modular, so we can attach and detach any model we want. The third parties are free to build their models using the API. Currently, we have 3 content providers in our implementation, which are photographs from Flickr, okay, defined and shot in a certain region. The choice of Flickr was driven by a bit of aspects, and I will talk about it later. The webcams installed in alpine regions, which has a big advantage and some disadvantages with respect to the photographs. The advantages are the fact that webcams provide an extremely high temporal resolution with respect to photographs, okay? And the disadvantage is that the spatial resolution is obviously a bit low because the webcams are there and the photographs continue to come from a bit every part of the world. And the third content provider are the photographs of the user itself. So I will show you in a moment. We will have some kind of web portal that do provide an interface to all this stuff, okay? And it acts like a specialized photo sharing website to engage the users and to produce this content. And so users are free to upload their own photographs to be analyzed together with all the crowded data. The content consumers of this data can be both environmental institutes or environmental models that use this data in their prediction, or once again also from the end users that just use the information we added to the photograph for entertainment and personal purposes. So what actually we add to these images is, given a geotagged image, we do not know where the photographer were looking at, so we actually do identify the orientation of the image during the shot and the position, the exact position of mountain peaks present on it. And then we do a pixel level snow classification. Okay, so we analyze the snow on the image, where there is snow, where there is not, and we also aggregate it in some kind of snow indexes, snow aggregations, and we produce some kind of snow measurement trends from this image. So the first point is, how do we pick up Flickr images? So basically we crawl a certain alpine area from which we incrementally and constantly take every day all the new images we find, and we classify them as relative and non-relative. Where the positive image, so relative, is defined not in an extremely trivial way, so it's not enough to contain mountain or snow, but we define our question as, does an image contain a clear and significant mountain slope view, okay? So we don't looking for hills, we don't looking for a guy skiing with just white line of snow, but we're looking actually for some a bit significant mountain slope. What we did from the study of a sample of this data, what we were able to see is that the rate between the positive and negative photographs depends heavily on the elevation of the shot, elevation of the photographer during the shot, okay? So we can easily estimate the elevation, assuming that the guy was standing on the ground, by digital elevation models. The digital elevation models are nothing more than 3D models of the terrain. You can think about it, since you do image processing, like simply a satellite image where each pixel has an intensity based on its elevation, right? So we have just this image, and based on that we can imagine a 3D model. So for each photograph by GPS, we can instantly estimate the altitude. And we saw that this line goes even further, and the situation got worse with the elevation going down, that it was really hard to find positive images when the elevation goes under 500 meters. Oh, sorry for the meters, by the way. I hope it's still clear enough. Is it a problem for someone?
Wow, there's only 2 of us who are born in
Okay.
in a country that doesn't use mile
Okay.
meters, so I think we're fine.
Okay, great. And basically what we discovered is that we can have, even with an amazing classifier, going with such small percentage of positive images was really bad. So the data set was so unbalanced that basically The classifier worked really bad, and the best politics for any classifier was predict negative, basically, right? Because of the problem. So we decided to keep only images, only photographs shot above a certain altitude, in particular 600 meters. So it's pretty here, where basically the percentage of the positive to negative is like 1 to 3, which is balanced enough for a classifier to do well. And then we just trained a binary classifier on these images. I think that there will be nothing extremely new to everybody inside this room, but still we used both vector visual words and visual vector, some descriptors, both local and global, like SIFT, dense SIFT, scene, gist, hot. And the adoption of spatial histogram was actually a good idea, because you can imagine that a photograph of a mountain is strongly characterized by vertical prior, let's say. So we just used vertical bands of spatial histogram, which improved significantly the result. And the classifier was tested on 1,600 samples, trained, sorry, on 1,600 samples, and tested on 700, obtaining the performance of like 95%, which is good enough, and especially considering the fact, taking a step back, sorry, that the question is pretty subjective, okay? So what does significant and clear mountain slope view means? It depends from person to person, and in particular, almost 13% of the annotators were, almost 13% of the photographs did not obtain an agreement, the notation between the annotators. So we have 95% of accuracy with 13% of non-agreement on the notation, and we believe that it will be pretty hard to go above this, just for the fact that the task becomes unclear to even to the humans, let's say. So there is just a bit of subjectivity inside.
So did you have a definition for what clear view of mountain slope looks like? Does that mean like I have to see the ridge? If I don't, do I have to see the ridge of the mountain or not?
I have to see a ridge, and it have to be a mountain. It not have to be a hill. It have to be a significant portion of the mountain. Obviously, this introduced the subjectivity, so we don't have a clear definition. Otherwise, we would not have subjectivity. But yes, yeah.
Right, but I need to see the ridge. I need to see the top of the mountain.
Yeah. So, or at least a slope. Let's say a good portion of the slope.
A good portion.
So here I should have this interface, which is kind of, it's not an interface for the end user, but it's kind of the debug interface for the crawler itself, where the crawler reports how it is going. And what we see is the area that we are crawling. It's well, basically northern Italy, Switzerland, a bit of Germany, and I think there is a heat map of the number of photographs retrieved for each region. Okay, I can filter it by date, by elevation range, also with the same technique. And what I can do is just to expect a certain area in a certain date interval with a certain granularity. So for example, if I go to Zermatt, where the Matterhorn is located, which is one of the highest, probably the most beautiful alpine mountain is, I have the statistics for each month, in this case, on how many images were classified positive, how many images were classified negative, and in gray, how many images were not classified. This can be due to the fact that it was shot in a low altitude, or because some optical information written in the EXIF container were missing. Okay, we will see in a couple of minutes why their pictures are useless for us. So when this information were missing, the images were discarded without being classified. I can also give a look at those images. Or for example, I ask for the positive photos of August 2015, and you see this. Okay, I can ask, I don't know, for the negative photographs of September, and you see this. Okay, so I can check the photographs with their score and so on. So passing to the other aspect of data mining, which are the webcams, we identified almost 2,000 webcams in the Alpine region, which depicts actually the mountains, depicts a significant slope of a mountain. And as I already said, the temporal frequency of these webcams is incredibly high with respect to the normal photograph crawling. So we have a webcam that produces an image every like 1 to 15 minutes. Yeah.
Do you use color information?
Sorry?
Do you use color information in your visual? In the previous slide, do you use color? Is it possible that white pixels dominate?
Yeah, sure. So whether we do use color information? Yeah. Yeah. Yeah, sure. And webcams also have a big problem with respect to the Flickr photographs, where normally one does not post a photo of only fog. Yeah? Okay, here we just take what comes, and being at such high altitudes, an incredible portion of photographs is affected by bad weather, which makes it unfeasible for further analysis. In the particular experiment we conducted, it was 67% of the images were not suitable for the analysis, so we definitely need some kind of filtering procedure, which in our case is pretty simple but effective one. So what we do is we extract the edge map from the image, then we see the edge inside the skyline neighborhood, and we assume that if the skyline is visible enough, which is defined basically by the number of rows that contains at least 1 pixel, and we can see it intuitively as the percentage of the skyline that is visible, we assume that the image is affected by good conditions, otherwise bad conditions. Obviously, it leaves a bit of space for small clouds, like going under the skyline and being undetected, but we will see in a moment how do we solve that problem. And here we operate on this ROC curve with, well, something a bit smaller of 90% of accuracy. And we choose a point actually with very low false positive rate with respect to sacrificing a bit of true positive rate, just because the images are really a lot, so we're ready to sacrifice a bit of true positive to reduce that.
So these webcams are like just ones that normal people have set up.
Exactly.
So how did you find them?
We started looking for them manually, which collected a couple of hundreds of those webcams, and then we also exploited some webcam datasets.
Okay.
So there are platforms that actually do contain the dataset of webcams with their positions and whatever. We adopted only the webcams that do interface a static URL of the image. Okay. There are a few portions of the webcams we did not include because they were it was too fancy to crawl, because they use hashing, a flash, and whatever. Yeah. So these webcams are only the static URL, and that's all. So what happens next is that you can imagine that the images from a webcam varies greatly during the day in terms of like shadows, solar glances, weather conditions, obstacles like can be small clouds, but can be also people, cars, and other moving objects in front of the camera. So what we do to reduce a bit this problem is that we assume that the snow will not vary greatly during the same day, so we don't see a webcam like a source of a lot of daily images. We see any webcam as a source of only one daily images, which is taken just as an aggregation of all the images, as median aggregation pixel by pixel. Okay. So here you can see an example of the 11 images shot by a webcam. As you can see, the shadows, the sun, the solar glances vary a lot. And if we aggregate them all, well, the weather becomes pretty standard, the obstacles are faded away, and the situation is much better. We also deal with trembling of the cameras because it happens a lot. You can imagine that it's pretty extreme conditions to webcam to work, okay? And often they're not fixed to something stable like houses, but to some casual sticks or whatever. And there is a lot of wind, so the trembling can be a problem. And we actually apply a cross-correlation procedure on the edge of the image, just to slightly lie them between each other to avoid trembling. And so this is, let's say, the final image that every day is produced by the webcam, or no image is produced if all the images of the day are are bad weather conditions, which happens a lot. We can actually have holes of 1 or more than 1 days. Because actually it's terrible. Okay, we know we go to the mountains when the weather is good, but until you look at the data set, you have no idea of how terrible the weather in mountains are. It's like almost always bad. Okay, so I'll start by showing you now a bit of the portal, just to give you an idea of what it means. So please forgive the fact that it's an closed alpha version, so there are no contents and there is not much graphics. Okay, so please forgive me for that. And basically, we said that it's some kind of photo sharing platform that contains information about all the media that we can access, that we can use also with our own information. So to make an example, this is me in Denver 2 days ago. Okay, I went to the Rocky Mountains National Park. It was really amazing, and this is a photo I took. It has the GPS inside it, the GPS tag, because I took it from the phone, so I can upload it to the website. Who's my user? Okay, now here we have some basic information about the photo, the GPS, and whatever. You can see the status being updated from time to time. Now it says that he's looking for alignment, so we will let him a couple of seconds or minutes to do it. Meanwhile, well, I'll continue with the, so we have. Meanwhile, I can just explore all the media I have here, okay? So I can see on the map or in the gallery all the images I have. I can filter them by type, like only webcams or only photographs. Whatever, I can see my photographs, I can see everybody's photographs. I can go inside and explore the area. I can filter it by altitude, okay? So if I put the high altitude, I see only images shot really in high positions. I can look also for mountain peaks, okay? So I can look for photographs containing a certain mountain peak. We will see in a moment how it is possible, and well, also by a date. So here basically I see all the information the SnowWatch platform has. In a perfect vision, in our vision, we would like one day this to contain all the images available about the mountains of the Alps. Okay, so every image on the web which is related to mountains, is related to snow information, is inside here available for analysis. Well, we are working obviously on the Alps, and now I guess if we move here, we will have, well, one lonely photograph here, which is the first one. Okay, so that's a great news. So coming back, what is happening in this moment in the platform with my photograph is that the photograph that has geotag must be identified as orientation. Okay, so we have to identify where I will looking at. We have to identify which are the mountains on that. How we can do it in several steps. So the first is we take this digital elevation model, okay, as I just said, just imagine it as a matrix of altitudes, like a grid of altitudes. And we can simulate what terrain we should see from the point of view where the photo was shot at. It's some kind of not so difficult computer or graphics program, right? Like a video game, just to generate this view. We generate it as 360 degrees view, so you can see it as a cylinder basically, okay, wrapped in front around the virtual photographer, and it looks like something like that. Okay, it's much longer than that. This, I think, there's a small portion. You can imagine it very, very long, and as it was closed as a cylinder. So this is the photo of the Matterhorn in Germany, and this is the corresponding panorama, what we call panorama. And very important point to highlight is that when we generate this, basically we can not only generate this image beautiful to see, but for each point we can generate all the metadata we want, okay? We know exactly the coordinate of this pixel, we know how high it is, we know how far from me it is, we know the inclination, we know whatever. So basically there are no limitations with what metadata you can enrich each pixel of this. And if we align correctly this photograph to this panorama, basically we translate all that information for each pixel to all information for this pixel. Okay? for each pixel of the photo, I can know everything I know for this pixel. And obviously, when I construct this, I know also when mountain pixels are placed, because it's a public dataset, and I just drop these coordinates and project them on my 3D model. And when I overlap it, I can see also the same information in the photo. So if I know that this is Matterhorn, I will know that this is Matterhorn as long as it's aligned correctly. The second step, very important, you can imagine that we have to scale it, okay? Because if we want to find an overlap between them, we have to scale the photograph or the panorama in the way that they have the same pixel dimension for the same objects. Okay, so the same degree per pixel dimension should be equal. Unless we have a scale invariant algorithm, which we do not have, we have to do this. This can be achieved by estimating the field of view of the camera. Okay? I'm not an expert in optical cameras, but from my ignorant point of view, just the Pythagoras theorem, right? Because we have the focal length, the distance between the sensors and the lens, and we have the sensor width. So if we apply the theorem on this, we can easily find this angle, which is basically the field of view. And once I know the field of view, I just scale it with a proportion, because I know that the field of view of the panorama is 360 degrees. The focal length is the information usually stored in the EXIF. Okay, nowadays every camera do it, and that's the reason why we discard the photographs when we don't have this information, because we're not able to find the correct scale. The sensor width it's much more tricky, because it's not written inside the EXIF, but it's a property of the camera. Okay, and the camera model and manufacturer are instead written inside the EXIF information. So what we have are large data sets of sensors. So for each camera, for each model, we know how big the sensor is. It's not such a trivial problem. Sometimes it's the failure and it's the bottleneck of some images, just because these data sets are unofficial, and sometimes the names of the cameras, some annotations, some acronyms are different. So sometimes it brings us to estimating wrong the field of view. But still, in almost all the cases, it works fine, and we're able to scale it exactly to the correct factor. Third step is we extract the edges from both of them. Okay, so you can imagine that the photo and the panorama share no common points except their shape. One is a photograph, other one is a drawing. So they have different colors, they have different textures, they have different features, they have different everything. The only thing they have in common are the shapes and the contours of the slopes. So we extract the edges from both, and we want to align them in the way that they overlap in the best way possible. Which brings us to the second problem, which is filtering these edges. You can imagine that all the edges which do belong to the photo and do not belong to the panorama are noisy edges, okay? Because they will just penalize our alignment. So this stone, for example, having this stone is penalization, because I will not have a stone here, and this edge will contribute negatively to my image. Furthermore, mountains are extremely edge-poor objects. They have only slopes. Meanwhile, we have extremely edge-rich objects, like you think about trees with leaves, or think about a person in the foreground with all the details of the West and whatever. So, for example, here is the estimation of what edges are noise and what edges are real ones. Okay, and you see that the noise edges are really a lot. We estimated the percentage of the noise edges being between 95 and 90% on the image. Okay, so if we do not remove them, the alignment is basically impossible. What we do currently now is pretty simple procedure. We just use the prior of the fact that the mountains are placed high on an image, so above the other objects. So we just prioritize the edge points, starting from the up and going down in each row, like in this way. This brings us obviously to a problem of the clouds, because if we have a cloud here which generate edges, applying this procedure would kill the whole algorithm, because we would have edges here and no edges here, So we apply also a skyline detection algorithm, okay? A computer vision skyline detection algorithm, which removes the edges placed on the sky and then prioritize the edge placed above the other. And finally, we do our match, which is a cross correlation, which is a vector cross correlation. So instead of looking simply for the best overlap in terms of edge strengths product, we add also the difference of the orientation between them. Okay, so two edges which intersect and goes in the same direction accounts for 1, two perpendicular edges accounts for 0, and if they're even more than difference more than perpendicular, they count as negative score to the total position. Okay, so it's the simple formula of the correlation with the cosine inside. So it's a vector cross correlation technique. And in this way, we basically find the best overlap between the two edge maps. There is some steps more, which I will not annoy you on global matching, which basically takes the top K candidates and apply other techniques on choosing the best one between them. But the big problem arises from the fact that despite this example, usually the photograph and the panorama does not overlap perfectly. Okay, that's quite a problem. It depends on several factors, such as the GPS errors, which happens, can happen a lot, and especially the DM precision, which in this case is like 1 point every 30 meters, which is not so bad, but can be better. And you can easily imagine that the problem of the overlap grows exponentially when we are high to some mountains low. Okay, so when we are far from the mountains, there on GPS it's not so bad. When you have a slope in front of us, just missing 20 meters on the GPS will generate a completely different image in front of us. So what is done is when this global overlap is performed, we perform a peak alignment on singular and on each peak. It's the same application of vector cross correlation. We just, sorry for the coloring, it's very bad. But once we have an alignment, we just take the patch, okay, around each peak and the panorama. This can be barely seen, but we apply the vector cross correlation on each peak, okay, on each peak neighborhood. So in other words, from here, each peak is free to move about a certain distance to being overlapped better to the panorama, and that's it. Okay, we tested it on a data set of public photographs with the 75% of correct orientation estimation. By correct orientation estimation, it means that the error is inside 4 degrees, I guess, of orientation. This percentage goes a bit up when there is no clouds, okay, because the skyline algorithm clearly is not unfathomable. Sometimes it compromises the good performance, and it grows really well when there is an absence of nearby mountains, okay, because as I explained, it can be a huge problem. So turning back to our photograph that we do upload it should be ready now, I guess. Yeah, it is. It says that he found an alignment, so from now on I can reach the photograph, for example, with the peaks, okay? So I see the mountain peaks on my picture, so I can, for each of them, I see what it is, how distant it is from me, what is his altitude. Okay, so this mountain shot in Chiquita and, oh my God, Fairchild Mountain. If I'm not happy with this alignment and I think that it's wrong, or I can just, or I want to adjust it, because actually in this case it's good, but it can be some pixels better, or maybe it's completely wrong, or maybe I just want to see how this alignment was obtained. I can go to the alignment page and see myself what's happening here. You can see that there is actually also the field of view, which is basically the zoom, okay, which I can change if I consider it to be wrong, or I can change it when the field of view is not available. So if I upload the photograph without EXIF information, it will not perform the alignment. It will stop and says, sorry, but I don't have information for the field of view, so you will have to align it manually by choosing the right zoom. And here I can see actually the alignment, what we were speaking about. You see here, we can see much better the problem I was speaking about. So this alignment is not perfect, but probably there is no perfect alignment, because here the left side is aligned pretty good, and then it starts drifting away, and obviously if I align this part, well, the left part will start drifting away too. Okay, so there is no way to translate this image with respect to panorama to get it perfectly aligned to the terrain. So the user in this case has the right to perform a nonlinear warping as long as I adjust one peak perfectly to the photo. I can fix it and just perform nonlinear warping on the image. Okay, so I can just pick it and scratch and put it towards the mountain, and then I just save it.
Is this problem comes from the camera?
Sorry?
Like the user's camera is different from the, like the camera has the shape to portray the image, so your alignment will be different from the panorama.
Well, for sure, one of the imperfections can derive from the fact that it's a perspective view, okay, and we don't know exactly how much does it change the image. Usually when the panorama is generated, it's generated as a lot of slices of the view with some small field of view, okay, so we don't generate panorama as like 4 pieces of 80 degrees or whatever, because that would be too much distortion on the sides of the image. But it's true that if we use slices like 10-15 degrees, basically there is no distortion in the perspective, and the panorama is basically continuous. But still, yes, the photograph has its own field of view, it's its own perspective. Let's say to be really perfectly correct, we should not have a panorama, but hundreds of pieces of panorama, each one generated with the same field of view of this one pointed in some direction. Okay, that would be perfectly reasonable and precise, but still it's computational and feasible.
But can you like do something with the panorama to according to the field of view of the camera?
We cannot, because we don't know where the photograph is looking at. Okay, so the point is that so what you're saying is that we should keep it good and apply a bit of distortion here and here, right? But we don't know that it's placed here.
Oh, yeah.
So that was I saying, we can generate thousands of panoramas, each one with a certain field of view centered in a certain point, okay? But that would basically blocks us from using the fast Fourier transform for the cross correlation.
Yeah. Like doing online, right? So whenever a user's image, whenever an image comes, then you, according to the information of this image, you do something.
You mean in the interface?
It's like a dynamic.
I think she means like, could you, when you see an image where you've decided, okay, this panorama is important, so now I'll invest the time in chopping it up into 1,000 little pieces. Like, would that be feasible to do?
Is it necessary?
Yeah, is it necessary? Is it good?
Well, it's not, let's say, so much necessary for one case, and the fact that if we would perform cross-correlation in space domain, that would probably do not cost too much, apart from generating panoramas, which is actually costly, but having a lot of panoramas in spatial domain probably would do the same. It was just enough to substitute one piece with another, but in Fourier domain, actually, maybe I need to think about it, but at first thought, I don't think it is possible, because we need one matrix, one image, and we apply cross-correlation in Fourier domain on it. So I don't think it's feasible. And basically, if we switch from Fourier domain, from the frequency domain to the spatial domain, we will pay a lot of price. Also with one image, it takes really an incredible amount of time. So the dimensions of the image basically does not allow us to work in spatial. Okay?
So when you mentioned you got something like 75% correct orientation, Does that mean the other 25% were wrong, or does that mean the other 25% were basically it said, I don't know because they don't have enough information?
Well, it means they were wrong. Currently, one of, let's say, directions of the work is working on I don't know aspect. Yes, that's still an open question. It's an interesting issue. Okay, so once we identified the photograph, we actually have to analyze the snow on it. Okay, and here I reported an example. I took one image from a webcam. I extracted 7 patches from it of 7 by 7 pixels, and just intuitively, in your opinion, what are snow and what are ground? Without looking at the bottom, I didn't blurred it, but still don't look. So if you would be a pixel classifier.
Let's see. All right, I'll do it. 2 and 7 or something, I guess.
2 and 7.
Yeah.
Let's see. Well, 2 and 7 are
2
snow.
and 7 is snow. Okay, so I wasn't so bad. But
Yeah,
the
but
I'm
still also
missing
3 and
some.
4 are snow.
Yeah.
Even being basically the same color ground here of 5 and 6, okay? So you can check on the image later, so you can see that it's not, the pixel level snow classification is not just going with the intensity threshold of a pixel, and here we are speaking about the same image. So look how many problems we have from the shadows, and it's the usual like images of illusions, of optical illusions, you know. What we have is that the ground point illuminated by the sun can be easily brighter than a snow point covered by shadows. So try to imagine on different images how big the difference would be. And so we tried several algorithms for pixel level classification, already presented in the literature. Some are just naive and heuristics. Some are unsupervised approach like GMM. We tried also a supervised approach for this problem, and we annotated 59 images, which seems a small number, but annotation here is pixel-wise. Okay, so it results in almost like 7 millions of pixels. That was a good data set, and we trained a random forest classifier on it, obtaining something like 90% of total accuracy on pixel level classification, outperforming other methods. Well, it's not such a glory. They were not supervised, clearly, but still, we show that there is much reason to use supervised classifier in this problem. And well, once we have these snow masks, what we shall do is to extract some kind of snow indexes from this snow mask, right? And here I will show you the last example of an image which has been processed with snow, which is my one here near Chamonix. Here I can yes turn on the peaks, so there is one here which is not visible very good, but there is actually a small mountain in front and one here. But even more, I can turn on the snow mask, so what the algorithm predicts for each pixel, okay, which is river level snow mask, so split it in sky, snow and ground. Sky here identified simply by the alignment, okay, so with inside the panorama we know where the sky is, so we know it also here. In fact, you see that there is a bit of imperfection. For example, this band, which is sky on an image, is still considered terrain because the alignment said so, and so it has been classified like as snow. And for each point, I can see whether it is sky, that it is sky, and if it is something not sky, I see whether it is terrain and snow, and for each pixel, I see the estimated distance from me, and also the estimated altitude, okay? This information we can get the panorama line. So somehow the portal transforms the simple photo sharing in enriched images with ecological and environmental information about each pixel. And as we said, the snow indexes that we can compute can be varied. They can vary from snow indexes that have intuitive, let's say, intuitive interpretation, like, let me see. where it's a webcam in an Italian city, Bormio, which analyzed for 3 months. And the snow index here is the estimated snow altitude, so the minimum altitude of where snow is present, okay? So for each day we have a lot of shots that are aggregated in a median shot, then this snow mask is estimated on that mountain, and what we calculate is some kind of snow index vector for 10 bands, and for each band we calculate how much percentage of snow was covered, and with simple heuristics we just cut the altitude inside the first band that has not enough snow and is considered threshold. So we have some sort of threshold that is maybe 10%, and when the band does not reach 10%, we say that this snow altitude is inside the previous band, and we assign the altitude based on the percentage. So here we have some kind of trend of the snow altitude growth during this summer. And as a proof of concept, actually, we compared it with the air temperature of a station registered nearby, which give, well, pretty good results. Even there is no perfect correlation, there is pretty strong temporal correlation in the sense that each time there is a peak of temperature, which is red, we have actually snow line going up. So basically the snow is melting after reaching this altitude of 3,000 something, which is the height of the mountain. It means basically the snow disappeared at all. But this is kind of, let's say, toy example, and the snow indexes can be non-intuitively interpretable. So we can just assign, for example, to each pixel one score, or we can assign the score based on the altitude, based on its area, on the distance, or whatever. But the problem is actually, which is a fundamental problem, is on all this area of environmental monitoring for us that do propose new methods, is to prove actually the utility of these measurements. Okay, so up to now we have shown all the results that states that from objective point of view the algorithms do perform well, from computer vision point of view the algorithms do perform well, but still a reviewer can always say, and they do, I don't think it's useful. Okay, so it's true that you proved that you're able to extract correctly the snow information, but I think that it will be environmentally useless. And proving that point is extremely hard, but is also necessary to be considered, let's say, with these aspects. And it's hard because we don't have direct ground truth. First of all, we would like to prove the fact that this data could improve the state-of-the-art environmental estimation, and that means that we do not have ground truth, okay? Because the ground truth that it's used in these works usually is the state-of-the-art estimation from the ground sensors and whatever. So a small parenthesis in this next slides, I will use as benchmark the ARPA, which is the Italian APA, okay? It's Italian Environmental Protection Agency, which do perform snow estimates with pretty barbarian methods. I will explain you how. So if the American colleagues of APA do better, please do not feel offended by this. So I will concentrate on one use case. But I think that the general idea could apply to every method. So we don't have the direct ground truth because we would like to outperform someone which is considered to be the best, and there is no gold standard above us. And often we don't measure the same thing, so we can take from the ground stations the snow altitude, right? But we cannot estimate the snow altitude from our images. We have some kind of snow indexes that are not intuitively interpretable, and we have no way to measure direct ground truth, how we are used to do in computer science, right? The idea is to measure the practical input and the practical utility with respect to some environmental model. Okay, what does it mean? It means that it can be potentially any environmental model of potentially any purpose as long as it benefits from snow measurements and probably is using official snow measurements right now. Okay, so just to give you an idea, the Italian APA just produces snow masks of the whole region where I live, which are obtained in pretty basic and trivial methods, because they have like 20 measurement stations dispersed in the regions, which are very few. It's a very low number, but they cost a lot, so they don't have any more. They take these 20 points every day and then linearly interpolate them in the whole region. Okay, and consider the fact that snow is an extremely difficult dynamics, so it's extremely difficult to model. You linearly interpolate measures of hundreds of kilometers. That makes those measurements basically random as soon as you go far from the station, okay? Without even accounting the altitude of the point. So what we did is we found a model which is used by our colleagues in Politecnico in environmental engineering, okay? And they work on common lake water management. I have really low knowledge in environmental monitoring, but I will try to explain you with, as long as I understand it, with basic words. Okay. So the common lake, where actually our campus of it's a small campus of our university is located at. Besides being famous for George Clooney's villas and whatever, it's also a very big lake. It's the deepest in Europe. It contains a lot of water, and it's extremely important for the agriculture of the whole region. What we have is that the basin of the lake is extremely big. It's something like this. Okay, so even these mountains actually contribute to its basin, and we have the water that comes down from the mountains with the snow, and we have some guy which can open and close water in front of the lake. Okay? And every day he makes a decision. He opens or closes that water. And what is the point? If you open it too much, or you open it and a lot of water comes from the mountains, you have this. This is one of the main square of my city. This happens like once every 2-3 years, okay? And well, it was really extreme here, but still there is a big flood because you put water, mountains gave water, that's the result. The opposite way is that if you don't give water, and neither the mountains do, you have this. You have no water, okay? And almost every summer we have a period when you're forbidden to give water, for example, to your plants during the day, and you will be fined for this because there is no sufficient water in the city, okay? So what our colleagues are working at is a supervised trained model which do decide whether to put the water into the lake or not and how much. And you can imagine that one of the most important input features of this model is the estimation of the snow, okay? So what we did is we added to their model also our virtual snow observations to see how the model would react to it and to see how was our data useful to that model. I have to make another small parenthesis. In computer science, we usually work with a lot of data, and we are happy when the data is big, right? We don't care if we took it in 1 week, but if we have millions of data, we are happy. In environmental engineering, unfortunately, they do not care much about a lot of data, but time span of the data, okay? They can have something per day, but they want 10 years of that. So we have a big problem here by the fact that we don't have enough time span of this data. We started doing all this stuff something like a year ago, and we don't have enough time data. What we were able to do is for one of our webcams, we were able to retrieve a huge historical data set from the owner, okay, and we went like 4 years back with all the data of that webcam. So we tried with this, let's say, insane idea of trying to input only one webcam out of all the samples. So we extracted the snow indexes during these 4 years from one single webcam, which is placed actually extremely far from the lake, but still it's inside the basin, okay? So even if it seems impossible, the water from here actually goes here some way. And we had one single webcam producing some series of features, and that's all, and we fed it to their model to see how it reacts. First of all, we removed the snow estimation of the APA, okay, and we had our input feature, and the result was that it was to simulate the fact that you don't have the official prediction. Let's say you have to use the other one, ours. The result was that the first feature selected was day of the year, and it makes sense, okay? That's clearly the, the best way to predict it. The day of the year counts. The second feature instead selected was our snow feature, which was basically the same utility of the day of the year, even a bit less, but still adding the predictions obtained from one single webcam far from the lake improved the performance of their platform by 100%. Okay, and that was really a huge boost. Here we can see the comparison with respect actually to the APA data. So since we are talking about trade-off problem, clearly there is no one solution, no one error metric, okay? It depends on our desired target solution. So how much irrigation problems we're ready to tolerate with respect to flooding problems. So there is no the best one, unique. But still, if you look at red, we, and green, they, we cannot state that we do better than official snow predictions, but it's also true that there are some target solutions that are, let's say, make sense where our estimation is actually improves and is better. And all this, I repeat, I said the point is obtained for now with one single web, okay? And still, there is a proof of concept of, from practical utility point of view, that those data actually carries environmental utility. So just to conclude, I don't know, what's the timing? Am I good with the timing?
Yeah, we have maybe a couple minutes for if you
yeah, sure,
conclude now,
okay.
then we can.
So I just conclude here. So the current work goes on obviously improving all the results if we can. We want to expand tests on environmental impacts, okay? This is hard to do because it requires a strict collaboration with environmental engineers, of course. No IT engineer can do it on his own. You need some environmental model, you need to work on it, and they have completely different ways of working, whatever, so it's pretty hard to find data, to find enough time spent and whatever. Another current aspect we are working at is the real-time augmented mobility application, okay, that uses pretty the same algorithms to identify the mountains in real time, and it would act as entertainment application where you can see the mountains in front of you, but also when you take the photographs, we could grab the photographs and they are already orientated and annotated, which would be a great advantage for our use. So it would be a new source of data, let's say hidden from an entertainment point of view to the users, which brings actually quite a lot of challenge because of the reduced power. We have big advantages like the sensors, okay, of the camera, which gives an idea of the orientation, but still are not enough. And the big disadvantage is that the power is really reduced. And to show you just, I have some, I think, just prototype video. So consider that there are actually competitors. There are actually some competitors on the market, but they use only the sensors, okay, to provide this. This is a basic computer graphics problem. You just have to project it on the screen, which has a lot of disadvantages. First of all, obviously it's imprecise due to the sensor error. Secondary, often it's not able to understand whether a peak is visible or not in terms of other mountains, okay? You need a digital model. Third, it's for sure unable to understand whether the peak is not visible for temporary obstacles like your friend in front of your camera, while with these techniques, when we challenge the problem of I don't know, that could be the solution, let's say. And fourth, it's, let's say, well, it derives from the past too. It's really hard to understand where what you are bound to show as a mountain has no sense. For example, this application often, when you point it to the the ground, they found something. I don't know whether they are Australian peaks or what happens, but still the sensors go crazy and you're done. So this is a prototype we're working at. This is me at Como Lake. And here is what the sensors would say in that moment, okay? It's not bad here. And actually, to be in a sensor, the error is pretty small. I had a brand new phone here to test it, and it was pretty good. It can do much worse than that, but still it's not perfect. So what happens here is that alignment procedure applied to each peak, and when it's colored green, it means that it's actually fixed with the computer vision application. Okay, so it actually goes exactly to each point with a great precision. Now I will move a bit the phone, and the peaks are following the video with a bit of delay. Okay, it's not the error of the estimation, it's just the delay of the algorithm. So it takes a while to process, and there are two solutions to this. Or you just wait each frame for the position, which makes the experience awful, or the icons are late with respect to the video. Okay, so that's the point we're working on currently. We want to make it really much quicker, but well, for now it's just this, and it follows a bit late the movement of the phone, but still. Okay. So as you can see, it's pretty successful in not giving false positives. There was one for a second on the ground. And well, the future areas we would like to use are to actually expand the area of environmental monitoring, apply the similar techniques. As I said, we're currently starting to work with not, the projects are not mature yet, but we're starting to work on vegetation, with also a challenging problem, and water, which for now, from computer vision point of view, seems a terrible problem, okay, because identifying water on an image, besides being studied really few works, and I understood why it's a nightmare, because the water basically reflects everything and adapts as a camera to any surface. But we're trying to monitor the rivers with webcams that actually there are placed by public people, like for example for fishing and for monitoring of the waters and whatever, on the vegetation monitoring. And that we would like also to try orthophotos, that is basically projecting the image on the digital elevation model. Okay, that would basically allow us to obtain some kind of fake satellite images, which are not satellite but obtained by the aggregation of the images, and also new snow indexes, because clearly a bit of environmental knowledge there would benefit a lot. And that's all. If you have any questions, please.
Great. Anyone have a quick question? We can follow up also afterwards. Oh yeah.
Yeah. So I'm a student, PhD student, working with Professor Fedorov on environmental modeling.
Yeah.
And we are going to meet tomorrow. So I see that the sensor, the looking at the computer vision, using computer vision to detect the snow and tie that into a sensor, that is like very advanced compared to the other sensors that I've seen that they're used in deploying in the field. So, so of course that in environmental science they are heavily using the satellite image, the sensing data, which I think can more accurately detect the snow. But then they don't have the high time frequencies that you can achieve. And also the sensors that I happen to know that they deploy one of the like small pod into the field and then collect the sunshine, the rain, or even the snow. But it is expensive and also requires like the transmission from the pod to whatever the receiver.
Yeah.
And it poses a problem if you have like a big mountain area and you cannot afford going to the mountains and deploying the things. And looking at from a small camera and you can cover a wide area, I think that's more efficient and cheaper and also like covers wider area than those sensors.
Yeah, actually there has been a bit of work in that direction from environmental point of view where they deployed their own cameras, which bring some advantages, but still is, let's say, ad hoc campaigns with ad hoc placed webcams. It requires still money to build it, to place it, and whatever, and you can not have a large coverage. Okay, so we actually been inspired from that work, and that we moved to the user-generated content, which brings a lot of problems because you don't choose anything. You just take what you have from the people, and actually brings a lot of new challenges and problems. But it would allow you to really increment a lot the area you're monitored and also the time and spatial frequency.
And it would be more interesting if you can expand that from just knowing to other kind of classification.
Yeah,
like,
sure.
Like the classification of type of crops like that, or like the area of forest, something.
Yeah, in fact, the vegetation is one of the current areas we're deviating at to apply, basically, trying to apply the same techniques. It's a bit more complicated if you don't have mountains, because of the orientation challenge, clearly. Still, the vegetation can be applied also on the mountain data set, because you have vegetation at the low altitude in the mountains. Or we should, let's say, come down to short range. Okay, so also I think a couple of works of Professor Crandall are based on that assumption, clearly, also on snow monitoring, because if I assume that I'm a short-based, I have a short-based site, well, it's enough to assume that the measurement is placed inside that GPS tag. Clearly here I can look at the mountain placed 30 kilometers from me, so considering the GPS tag is not enough, I have to understand which mountain I'm looking at.
Looking forward to the discussion.
Great, thanks.
All right, this is great. Thank you for coming. Thanks so much for visiting.
Thank you for your attention.
Good talk. Thank you.